Okay, good afternoon, everyone. Thank you very much for attending our virtual lab tour today. We're visiting the Human Robot Interaction Lab, which is an entirely new facility built last year thanks to our funding from the Welsh European Funding Office, the Welsh government, and Cardiff University. So this is one of the contributions IROHMS is making to the field by building this research facility and making it available across the whole university and also available to our collaborators from industry and the public sector. So as you know, IROHMS is a research center for AI, robotics, and human machine systems. So our focus is on this fascinating relationship between humans and robots. And IROHMS is a collaboration between three schools: engineering, computer science, and psychology. And this is a unique feature of our center. So we are very proud with this collaboration. So, sorry. I'd like to present those who will be presenting. I'd like to introduce those who will be presenting today. So I'm going to mention first Maryam. Maryam, I think she's in the corridor somewhere in the building.
Hello.
Hello. Maryam is has been working very hard on this virtual tour. She's the lab manager of this lab. She has gone through so much during the last few months um, with the COVID situation and everything else. She started her work at Cardiff in April, and until I think October, she wasn't even allowed to see the lab she was going to, or the room where the lab will be, the lab she'll be managing. But she will start her tour in a moment. I also want to introduce Abolfazl, who is a new lecturer in robotics, and Juan behind the camera, who is also a new lecturer in robotics. He started only a few months ago, and they're interested in this field. I'd like to introduce next Reda, who is next to, yes, he's helping Maryam with the tour, and he'll be moving the cameras and showing you the KO-bot robot a little bit later. And also Arpit, say hello.
Hello,
Please.
hello, hello, everyone.
Hi. He's also going to talk about some of the newest equipment in the lab a little bit later. Also, helping today, talking about their research, Harry, who is
Hi
working
everyone.
with the Siemens simulation software, fascinating software. I also want to introduce Stephanie Price. She is an undergraduate student, but she has done such a brilliant job with her project. So I decided, no, we should talk about opportunities in undergraduate project work as well, and how we try to convert some of our best students towards research, maybe in future. Stephanie will tell you about her simulation with autonomous car in a smart city environment. Fascinating. Then I want to introduce Tong and Francisco, who are going to talk about their PhD projects. They started just half a year ago. but they've made a lot of progress with the definition of their projects, etc. So we have a fascinating agenda, and the whole tour is facilitated by, of course, Jet Ruel, Jet, and Helen, our center manager. So thank you everyone for attending this tour. And Maryam, please tell us what you have prepared for us today.
Yeah, thank you, Rossi. So hello everyone, I'm Maryam, and together with Reda, we are here in the south wing of Queen's Building at the heart of the IROHMS engineering. So we have office of Professor Rossi here. We have PhD students' offices. Also, we have the center's headquarters. And at the end, we have the human-robot interaction lab. So welcome to our lab, and please follow me.
Hello everyone, and welcome to the Human Robot Interaction Lab virtual tour. I am Carol Buffour. And today, together with my friends, we are going to give you a glimpse into our world and what we do in our amazing lab. But first, allow me to begin with the robotic opening dance. Hopefully there are no professional dancers in the audience. Okay, let me pass you over to my colleagues before they shut me down.
Okay, so we had greetings from K-Robot 4. K-Robot is the service robot that is developed by Fraunhofer to support human in their daily life and also for healthcare. So this version is K-Robot 4, which is the fourth and the latest generation of K-Robot series developed by one of Fraunhofer's spin-off, Mojin Robotics. So this robot is a very advanced robot with 29 degrees of freedom and also with several built-in sensors. And the robot has 158 centimeter height, which is quite a large size for the robots of this kind. And the workload capacity of each arm, for example, is 3 kilograms. So it can carry 3 kilograms with 2 arms. The main components of the robot are the base, torso, head, and arms. Base is, in fact, a mobile robot which carries the body of the robot over it. And it has safety lasers around it, which will stop a robot if it gets too closer to an obstacle. And torso has 3 degrees of freedom, so it can bend, it can rotate, and it will cover large a variety of movements that is needed for these types of robot. It has a LED ring around the torso, which its color indicates the operating status of the robot. It has 3D cameras for environmental monitoring, and also another 3D cameras here for floor monitoring, and also 2 emergency stop in front and back. And for the head, we have a 15-inch touch screen display, which is used to interact with humans. It got 2 eyes for facial expression. Well, exactly the same as us with these face masks. And it also has a moving sensor in here. It's got a 3D camera as well for facial and also gesture recognition. It got speakers and microphone for speech processing. And finally, the robot has 2 arms. Each arm has 7 degrees of freedom, and the grabbers has 2 degrees of freedom. So these 2 arms with 1 finger hand on K-Robot 4 are used to have mechanical interaction with the objects in the environment. So let me pass it over to Reda to present the software and the simulator of the K-Robot.
Hi, just testing if you guys can hear me. Okay. So I figured I'd take you through my workflow when it comes to programming the Garabot. So this is a simulator, and like I said, we program it so that it's in a safer environment. So, and this is an IPython notebook that's also provided that will basically interactively run code. And again, this is very useful for testing purposes. And seeing as this runs as a main ROS node, I can also run some Python scripts, for instance, and I'll also be able to see the results of it immediately. But there are some drawbacks to this. For instance, it doesn't have any sound output. So in order to test speech, I would have to first test the actions on the robot, and then on the simulator, and then run it on the real robot so that I can basically sync any sort of speech. And another thing is that it doesn't necessarily indicate when there's a motion that might harm the robot. So that's just it's necessary for me to have care on my part to be able to basically tell if there's anything that might go wrong. And I think that's about it for the main parts. This is a remote emergency stop that's like on top of the 2 that are already on the robot. This is pretty useful in case the robot decides to go haywire and murder us all, but hopefully that's not going to happen anytime soon because, well, I'm not that good a programmer, but yeah, so thank you.
So thank you, Reda. So I would like to ask Professor Rossi to introduce the research priorities of the lab.
Thank you, Maryam. So this lab is mainly used by members of 2 working groups, obviously humans and robots, but also human-like AI, because what the main purpose of this lab is to study the relationships between humans and robots, but also to develop advanced abilities for robots to behave, learn, study, anticipate, predict human behavior better. So it's about people and robots working together. And these abilities for robots to be able to coexist and collaborate, they have to develop additional abilities, not just manipulating objects. We are working on difficult research problems like human intention recognition. So today we were discussing with Tong and Abolfazl this fascinating problem of this mutual understanding between surgeons and nurses in the operating theater. How do they build that mutual understanding? How do they maintain in the context of maintain it in the context of what they're doing? How can we train robots for certain tasks to assist people with the same degree of understanding of the task and the person there who needs support? So the main area for this lab is context-based reasoning. So providing the robot with context, giving the robot the abilities to reason within that context, and obviously collaborate with people. And this is a very, very ambitious research agenda. So we're going to show you a video. We have used this Wizard of Oz approach. So this is very much what we want to see in 5 to 10 years happening. And these are the problems we're currently working on. So the video was produced by Maryam, and you will see her and the care robot acting together in this video. Over to you, Maryam.
Thank you. Yes, so this is one of the work that we have done in the lab with Reda. And Jed, would you please run the video?
Hello.
Hello. Welcome to the HRI lab. May I help you?
I need to check if the risk assessment is done for this lab.
You can find the form in the red book. Would you like me to assist you in finding it?
Yes, please.
The last time I saw it, someone was checking in over there.
Oh, I can see something red over there.
Let me check. This is not the red book. It might be in the drawer where all the documents usually are.
Okay.
Oh, the drawers on the right are for equipment, and the middle ones are for storing lab documents.
All right. Thank you. Oh, it's locked.
Yes, I just got the key. Here you go.
Thank you. Oh, here's the red book.
Yes, a copy of the risk assessment form should be there.
Yes, it is. And everything looks good.
Is there anything else I can help you with?
No, thank you for your assistance.
My pleasure.
Goodbye.
Goodbye. Hope to see you soon.
So thank you, Jed. So the next piece of equipment that we're going to introduce from our lab is Viken motion tracking system. You can see the cameras around the lab. So Arpit has recorded a demo. Would you please run the next demo?
You've been wondering, why do I have these odd markers on my body? Let me explain you. These markers are actually called motion tracking markers. These markers need to be there on your body to track your motion. So for tracking our motion, we have video cameras, as you can see around the room. And one more important thing, we also have a video camera whose quality is really good. That's 1080p and 60 Hz. These video cameras are also very accurate and very precise. So while tracking your motion, you don't have to worry about anything. Just remember one thing, before turning on the cameras, just keep it on for 1 hour, and you also have to calibrate the cameras with these Juan. Let's see what I look like in the virtual environment. So let's start with the Viken Nexus software. So there are a lot of software that Viken provides, but here we have Viken Nexus. Let me zoom in a little bit so you can see it clearly. So here we have the forehead markers that I put on previously, that you saw on my body, and here we have the wrist markers. Yeah, so as you can see the trajectories where they are getting tracked from. So the blue lights are the trajectories we are getting tracked from. Here I have the torso markers, and these are my chest markers. So as you can see, these are getting tracked from all the directions. And I have also put the markers, like as you can see, this is a human body, a little bit looks like a human body, and my hands are outside. Let's run the pipeline.
Pipeline ended.
And you can see the whole skeleton. Now you can see properly like how it has been made and how it looks like actually. So let me play a little bit, and you can see a little bit of motion in my hands, because this is a pre-recorded trial, and I have a little bit of movements in my body. So yeah, that's my right hand, which is green, and that's my left hand and left leg, which is red, and that's my head. And let's go through another trial that we have. And here yeah, let's play. So here as you can see, I'm doing squats, and as you can see how precise and accurate these squats are. Like this motion tracking software and motion tracking hardware can detect your motion very precisely and very accurately. So now let's go through another trial that we have recorded previously. And yeah, so as you can also see, like there are a lot of unassigned markers. I will talk about them a little bit later. See, right now I'm waving my hand and in the all four directions. So as you can see, as you can see here, we are in the motion builder software by Autodesk, and here you can see the model right here that we can make using using like a skeleton. So the first four head markers that we used were we can make the head from that, and we can also make the motion of the head from that. As you can see, the head can move in any direction. Now we could go to the chest, because chest doesn't move, so it doesn't have that much movability. That's a torso, and we have separate leg parts. So as you can see that we have previously put a lot of markers on the thighs and ankle and wrist. So that was the markers for. Now I have made an animated character of the waving hand motion that you saw previously, and let's see what it looks like. Here we have our virtual agent. As you can see, my right hand waving and my left hand in the red, and that's our virtual agent.
So thank you, Arpit. So apart from the hardware that we have in the lab, we also have licensed for software such as Siemens plant simulation software. Harry has prepared a demo using that. So Jed, will you please run the next demo?
Hi, I'm Harry Alexopoulos. I'm working on manufacturing simulation and process optimization, and I will go through the manufacturing simulation software that is available in Human-Robot Interaction Lab and of course Cardiff Engineering School. We start with simulation at a plant level where focus can be on a production cell or the whole factory. This type of software assists in evaluating changes in the production flow, and in this video we can see Siemens plant simulation that can connect with Siemens controllers and monitoring systems to create a real-time representation of the factory, or as it is called, a digital twin. Apart from visualizing different scenarios, the true power of such simulation is the identification of bottlenecks or inefficiencies in a production and a prediction of how one change will affect the rest of the plant. The change may be introduction of a new machine or process, scheduled maintenance work, an incident, a key component fail, anything actually that may cause disruption. There are plenty of diagrams and statistics generated that make it easy to quickly assess multiple cases and produce a plan in advance in case something goes wrong. There are quite a few simulation packages in this category available. Lanner, Witness, Simio, AnyLogic are options to choose from depending on the study requirements. All of these packages offer similar analysis with, of course, different strengths and weaknesses. Now, zooming into process level simulation, we see a video from Siemens Process Simulate, part of the same suite as plant simulation. This category of software focuses on one process and simulates process-specific details. Since IROHMS is about human-robot collaboration, this is probably the closest package to simulate this collaboration. This software is very helpful in visualizing a production cell setup, identifying details that may hinder process efficiency, and also analyze ergonomics, analyze the human body stresses, and checking for dangers of collision or identifying situations that the robot has to slow down. We can see, for example, the volume that the robot operates in, so it is easy to define then space requirements and potential collisions with the environment. Finally, in the School of Engineering, we are also developing custom simulators. The one on the video is a next generation simulator for vertical milling. Here we see its web interface, which shows the process and displays the data captured from the machine's monitoring system. At the same time, the simulator calculates in the background the expected values and shows to the user the differences. The diagrams make it easier to spot unexpected events or trends, and there is ongoing work to further enhance the output in order to generate simulator suggestions. The main difference with traditional simulation is that this one is running the actual process in a virtual world and can therefore provide process data that is not being captured by the physical world sensors. In the back end, the simulator can run a process before it begins and provide an estimated monitoring output. It can also provide info about cutting tool usage, cutting forces, assist in determining process efficiency, and since this is a custom build, it can be extended to whatever the needs are. We have also enhanced the simulator with tools that allow for process analysis and show graphically what happened during the process, when, and which parameters were involved in this incident. We can then compare different runs of the process and see if this is a one-off event, if there is a pattern, or see if a specific machine behaves differently. It was a quick overview of the manufacturing simulation tools available in the lab. I'm happy to answer any questions and of course to work with whoever is interested in simulations, production digitalization or similar subjects. Thank you.
Okay, thank you, Harry. So the next presenter is Abolfazl, who's going to talk about the research potential using eye tracker and EEG headset. Abolfazl, it is over to you.
Yeah, thank you very much. So hello everyone, I am Abolfazl. As Rossi said, I'm a lecturer in the engineering school of Cardiff University and also a member of IROHMS team. So regarding the equipment, so we are in the process of buying two important devices for our lab. They should be here, they should be available here soon, hopefully in a month or two. So we are buying a 32-channel EEG system headset with the active electrode technology in order to observe human brain activity and analyze them in order to capture high-level factors such as intention and also emotion in different contexts when we are interacting with robots. So we are also buying a mobile eye tracking glasses to support our ongoing project on human perception and human attention in various human-robot interaction scenarios. So using these devices, our final aim is to explore the social and emotional dimension of human in interaction with robots, machine, or any pieces of technology. So our research is not limited to the social aspect of interaction. We are also interested to extend our research to the industrial context. So our aim is to develop the AI-based system for that which enables a safe, trustable, and autonomous industrial interaction with the industrial robot to have an efficient robot which is able to collaborate and interact with the human in the shared workspace and manufacturing industry. So if you are interested in our research, please do get in touch with us. We are happy to collaborate and support your research as well. Thank you very much.
Okay, thank you, Abolfazl. So finally, the last piece of equipment that we have in the lab is the Vive virtual reality headset. We have a short video from Arpit. Jed, would you please run the next video?
Hello everyone. Let's talk about another device here we have at Human Robot Interaction Lab, which helps us in human robot interaction. So here we have HTC Vive Pro. This is a standalone kit, which means it can actually work on its own. You don't need any external support to work on it. It is a virtual reality kit as well as augmented reality kit. But before putting this on, let me tell you some more things about the other stuff we have here. So these are actually called controllers, which I will show you in a minute in the virtual reality. So the one thing you have to keep in mind is these two detectors. These two detectors need to be in the range of where you are standing. So these two detectors need to be seeing you. So don't get out of their sight. If you go out of their sight, they won't detect you and the virtual reality won't work as expected. So let's put the headset on and let's see what it looks like. So as you can see here, I have the tracker, I have the controller, and it's such a nice view.
So thank you, Arpit. Let's continue with the students and academic project. So the first project is from Stephanie Price, which is on driverless car simulation. Jed, will you please run?
Hello, my name is Stephanie Price and I'm a mechanical engineering undergraduate at Cardiff University. For my dissertation project, I'm looking at explainable robotics and virtual reality. The specific scenario of this project involves driverless cars and how they interact with humans in a city-like environment. I'm using Unity to develop my scenario, and as you can see on the screen, the car that's being followed by the camera is a playable car, which I am controlling with the WASD keys, and I also use the spacebar for braking. The other car is a prototype of my AI driverless car, which is following a script and a pathing system that will allow it to drive around the city, or in this case, a flat terrain. My car can interact with the car, such as crashing into it, like that. When crashed into, the driverless car will then find the shortest route back onto its designated path. The cars are controlled by a number of features such as C# coding and physics, which allows them to interact. Once I had developed the preliminary cars for my scenario, I decided to create the urban environment in which they would be contained. I used an asset from the Unity Assets store called CityGen 3D, which helped me build an urban environment based around a map of New York. In this video, I'm going to take you for a short tour through my city, where you can see that it is populated with a various number of trees, buildings, bus stops, letterboxes, lakes, and other common things you find in a city. The city itself is quite large and will have to contain a number of different autonomous vehicles, as well as a player-controlled car and pedestrians. The next clip is a short demo of when I introduced my first player-controlled car into my city environment. I used an updated model with a nice sports car finish, which also had internal details and allowed for a first-person view as well as a third-person view. I used a script to allow the player to switch between these views to whatever is most comfortable for them. The purpose of this project is to allow the player, a human, to experience what it would be like driving around a busy city that's populated only by driverless cars. I think driverless cars will play a massive part in the future of society, so it's important to break down the barriers between human and AI connection. Driverless cars rely on machine learning and AI, which is why simulations that monitor how they interact with humans are so important. A driverless car can be trained to avoid all the obstacles it likes, but the one unpredictable part of its lifespan is how human drivers will interact with it. It can stop for a pedestrian, but it can't help if it gets rear-ended by a human driver that's driving behind it. This project is still in development, and the next steps involve furthering my code for the driverless cars and allowing them to detect and avoid obstacles such as the player car or traffic lights or pedestrians. I also need to add some finishing touches such as audio and weather and smaller things like brake lights and the steering wheel turning with the wheels. On the left is my scenario hierarchy, and on the right are the objects attached to the parent object of my player car. I'm going to open this script up and show you what actually went into coding the car to move like it does. As you can see, I have a number of functions for the braking, acceleration and turning of the car, including functions that allow the wheels to move and spin in relation to where the car is going. Thanks for listening to this brief demo on my dissertation project.
Okay, thank you, Stephanie. Very interesting demo. So the next presenter is Juan. Juan, please, over to you.
Yes, thank you. Do you see my screen and hear me well?
Yes.
Perfect. Okay, so yes, thank you for the introduction, Rossi, before. I'm also a new lecturer at Cardiff University. I'm part of the School of Engineering. My expertise is in robotics and different topics of robotics, but particularly in motion planning. So today I want to show two simple examples of what motion planning is about and two probably areas that are really popular these days. No, the first example is about autonomous driving. This is a project that I was a technical leader a couple of years ago for industry. And the idea was to provide a motion planner and the whole infrastructure to control an autonomous car in a parking scenario. So this is typically called in industry an automated valet parking case. So what we want to do here is basically we design a spot where we want our autonomous car to park, and the car will have to deal with unknown obstacles. No, so this is a really typical example of a robotics applications where we have everything that involves robotics. No, perception, like mapping and localization as well, and also motion planning and control. So we can see here how the car is avoiding the collision with the three actually unknown obstacles, the cars that are already parked in the parking lot, and how the vehicle is led to park in the designated spot. The second example, and it's also related to the areas that we have presented already, is an example of a full simulation of motion planning cases to do grasping of known objects in the environment. So for instance, imagine that we want to command the Carobot, the robot that was presented before, to go and grasp one of the objects. This is a really complicated task that cannot be solved directly with kinematics because the environment is assumed to be unknown and it's also unstructured. So what we will see here is motion planning techniques using start to goal region motion planning problem to control the dual arm system that we have here. What you are seeing on the right is a simulation that we also have from the Viking cameras. We can emulate the output of the Viking cameras to provide accurate information of position and orientation of the objects. What you will see here is that the sampling-based method is controlling both arms to actually go and grasp both objects. So we have been doing this kind of research for many years, and it's going closer and closer for different applications, including human-robot collaboration. So if you are interested in any of these topics, please just feel free to send me an email and get in contact with us. I will be happy to discuss more.
Thank you, Juan, for your presentation. So the next presenter is Tong. We have a pre-recorded video of him. Jed, would you please run the video?
Hello, everyone. My name is Tong from China, and I am a first-year PhD student at School of Engineering in Cardiff University. I was very interested in robots, which was miraculous technology for me when I was a child, but now I'm pleased to join the robotics research group and learn the knowledge of it. My research topic is human intention recognition, which is an interesting area. The robot is designed to serve or help people to complete tasks, even carry human beings. Therefore, human is a pivotal of the human-robot interaction. In psychology, intention refers to the ideas or plan that an individual wants to implement. So, the human intention recognition is also an important research field in human-robot interaction, which can help robots know what people may do next. We can imagine a scenario if you can use the eyesight or fingers, even thinking, to control the robot to take a cup of coffee for you. It will not only save us time, but also increase our happiness. Human intention recognition can be used in many fields. Wherever we are working, whenever we're having a rest, we want a robot to understand our intention. It is a small movement of robot, but a big step for human. That's what I want to focus on. I hope I can use the equipment of our lab central to complete my PhD project. Thank you for your listening.
So thank you, Tong. And finally, the last presentation is from Francisco, another PhD student.
Welcome to the IROHMS Human-Robot Interaction Lab virtual tour. My name is Francisco Munguia, and I am a PhD student at Cardiff University. Thank you for joining us today. My PhD project is about artificial intelligence for manual task handling. Facility for programming robots from non-expert users is a fundamental factor for the spread of robotics and everyday existence. One of the solutions to this problem is learning from demonstration. This is the reason because this thesis is aiming to develop an artificial intelligence to perform manual task handling and develop a method which successfully uses the context of the situations to guide the learning process of the robot. But how can we use the context in robotics? Ontologies are very well-known knowledge structures. For example, we can create an ontology of indoor places. There is a subclass of indoor place called kitchen with some characteristics like an oven, a fridge, and a blender. and the bedroom, which has a bed and a bureau. Now, if the robot perceives a bed and a bureau, it can infer that the context is related with a bedroom. Now let's say that our robot is watching a human shaking his head, and we want it to recognize if the human is saying yes or no. Then we can feed the function of the trajectory the human produced to when shake his head, and measure the mean square error, compared to the say no property, which results in a very high mean square error. But when we compute the mean square error compared to the say yes property, there is a low mean square error, and this way a robot can recognize what the human is doing. There are still many factors that must be considered, but I'm excited about solving as much problems as I can. Thanks for watching.
Okay, thank you, Francisco. You're quite on time based on agenda. We have a final demo by KRobot 4, but we would be happy to answer your questions, if any, before that. So let me check if there's any question. If not, we can go for the demo.
Yes, Maryam, let's see the demo, and colleagues will have time to think of a question.
I think that's good. So Jed, would you show it from my phone camera?
It is my turn again. Haha. I was standing here politely the whole time. So it is time for me to stretch my legs. Oh, I need arms. A few more of those and I am on my way to a six-pack. Well, thank you for joining us today. We hope that you enjoyed the tour as much as we enjoyed hosting it. We are really looking forward to meeting you and collaborating with you in the near future. We are at the end of the tour, so let us celebrate. Help yourself to a drink while I enjoy a warm glass of electrons. Yum yum. Goodbye.
Okay, we still have time for questions if there are any. We also discovered just now a new area of research, jokes which can be told by robots. Excellent start, Maryam and Reda and company. By the way, can you show the student office next door, Maryam, if you can?
Yeah, sure.
So some of our students haven't been in their offices at all. In fact, only once to visit the office. And it's we haven't made any special effort to make it tidier, but this is the space for the student, our students, and very conveniently next to the lab. So we have really good facilities. We expect to attract more students to Cardiff now once we have this fascinating laboratory. And we have plans for building a field robotics lab, because this technology is very much for indoor robotics. But we are planning to develop further the areas of research we've been talking about, bringing robotics to even more challenging problem areas like outdoor environments, etc. But do let us know any questions, anyone.
Yes, I have question if you allow me, please. Can you hear me?
Yeah, sure, please.
Hi, thank you, Rosie, very much. Hi. Thank you very much to you, Rosie, and your team. Really, that's very interesting work, and I'm so glad to see the School of Engineering building after quite a long time since I did my PhD in Cardiff University. Thank you very much. Yes, I have a question to Arpit, who showed a project related to human interaction with cameras and tags. The question is, Abid, did you think about the privacy issue because you are using a camera? So did you take the privacy issue in consideration? And also, it seems that the person has to wear many tags on his body. Also, did you think about these things? And what kind of application do you think your project could be used for, please?
Yeah, so I did think about the privacy. First, I'll answer your question about the privacy. So, well, the cameras are very, like, even if I record a video, you cannot export the video directly from the computer. Until and unless you connect a external drive, go to the lab and connect external drive, or until and unless you have access to that particular computer, you cannot access that. So privacy is not an issue here. About your other question, can you repeat your second question, please?
The person has to wear many tags, yes, on his body.
Yeah. So the thing is, like, because we have to train our model, or we have to in the end we have to train something, so we have to actually put something to the robot, or give instructions to the robot that this a person would be working like this, or her or his movements will be like this. So we have to put the tags before, but soon I think we will not have to put the tags. It can recognize the human motion directly, but currently we do have to put the tags because it's a motion tracking software, and it can only track motion through trackers.
So what is the alternative in that case? You said you might not use a tag in the future. So what will be the alternative?
So we might use AI using that. I have worked with some of the AIs that we have, like Radical AI. So it can just directly create your whole skeleton, but it is not as precise as we see. But yeah, we are still in the progress to work much better than.
And the last question is about the application. Where do you think your system could be used, please?
Yeah, so suppose I'll tell you a scenario. Okay, suppose I have we enter in a room, and we'll see the robot, and suddenly the robot will react to your reactions, because if you wave a hand, right? If we wave a hand, you have a motion of the hand, and the Viking tracking motion software will directly send the signals to the robot, and robot will respond to that that the person is waving. So respond back, wave hands, hello. He'll respond back, hello. And there can be many other applications to this, like suppose we are dancing, right? Because we don't have a lot of motion in the robot, but still, like, we can send signals, okay, dance, so he will dance with the other human being.
Yes, these are good examples, but Vicon is a research tool, so we're capturing motion to develop our understanding of different interactions. It's not for and then the simulation models will be applied to a different application scenario. So it's we don't envisage asking end users to wear these tags. You see what I mean?
Yes.
if you remember Alex's research, Alex Norwitz's research.
Yeah.
Alex's office was exactly here in this room, if you remember, a long time ago. But his work was on capturing human motion without sensors, that sort of tags, just by using vision and trying to abstract, the skeleton of the person, and then decide where the key points are, and then monitoring those imaginary points from the video. And this is his research was more about applications. However, we're talking about different levels of accuracy. So if you want to understand or to develop a very precise understanding of certain aspects of human motion, you probably need a system like that. An example is Kathy Holt's area of research, which is understanding medical conditions related to movement.
This is what I meant, yes, maybe for health
yes.
applications.
And trying to understand how these medical conditions develop over time, comparing movements before and after exercise in sport medicine, for example. So this is how they use it as an observational tool. Our focus is on developing models, new models, and new understanding of interactions. So we are going to develop new simulation models based on data from Vicon, and then feed that information to the robot so that we can develop its judgment.
So can I add a comment?
Yes, please.
Yeah, just to answer, you asked an alternative system for tracking the motion. This equipment is like working based on the optical cameras, right? So there are several other wearable systems that can be that work based on the IMU sensors, and they can accurately track your body. And they can be used in the health, sport, and science, and other fields of in engineering. Yes. Thanks.
In fact, will be so happy to cooperate in this because I have some ideas. Maybe I will contact you, Rosie, later on, because this is my area of interest. So maybe we can have some work together in this area. Thank you very much. That's very interesting.
Yeah, that would be great. Great.
Thank you.
Fantastic. Do we have any more questions? Any more questions from Stoffel? Did you see our digital twin? Harry's digital twin, I would say. I know we have representation from, hello, hi, Fleming.
Hey, Rossi, nice to see you again.
Hi.
Yeah, no, we did see it. I've been following closely, and Chris is here also. So we've reached out to a couple of people, and it's really exciting and interesting. So let's see where we can go with this.
Yeah, thank you very much.